Hello, this is Dr. Webb. Let's start this video by going back and thinking back about how we defined partial derivatives. So recall I have the partial derivative for some multiple variable function in terms of x here at a point x naught, y naught. And so we defined it in terms of something very familiar from Calc 1. It looks like the regular derivative formula. You take the function value at the two places, and then this dividing by the delta x on the bottom. Well, that delta x really is how far you've moved if you start at x naught, y naught and go to x naught plus delta x comma y naught, and then take the limit of all of this as delta x goes to 0. So this all looks very familiar. And we talked a little bit about how really what's going on here is if that's our f of x, that's our surface. If we have x naught, y naught right here, really what the partial derivative is doing is it's imagining taking a slice along a line parallel to the x-axis at x naught, y naught, slicing through that plane. That's going to give us a curve there, a one-dimensional thing, and then this partial derivative then is talking about the slope along there. Well, in the last video when we were talking about the chain rule, we did the same sort of thing, if you think about it. We talked about at the beginning, if you plug in some curve on the xy plane, how you can plug that into the function and find derivatives on it. And so we can also think about this partial derivative in terms of x as coming through by using the chain rule, using that line going along the x-axis. So what do I mean by that? So if we take the line x naught plus t y naught, right? So this is the line where the x value is changing, but the y value is always at y naught. So we're looking at this on the xy plane. So let's make that a little bit nicer looking. So this is our parameterized line going through here. When t is equal to 0, that's precisely when we're at x naught, y naught. Okay. And so then this partial derivative in terms of x at x naught, y naught, we can think about it as taking the derivative of the function along this line, plugging this parameterized line in, and then evaluating that derivative at 0. Right? And so if you don't believe me, let's go back and think about how we did the chain rule and take a look at this. Right? So we know that d dt of f of r of t, well, f of r of t, so that's really just shorthand for saying for the x-coordinate, we're plugging x naught plus t. For the y-coordinate, we're just plugging in the constant y naught. Right? And so this would be the partial in terms of x at x naught, y naught times x prime, but then the derivative of the x component in terms of t, so this would be dx dt. Well, x naught's a constant plus t, that derivative there is just 1. And so we'd have just a 1 there. Plus partial in terms of y at that point. Really, I should put in a plus t there and a plus t there. Better late than never. But then the partial, the derivative of y naught's just a constant, and so then that's equal to 0. Right? And so at the end of this, it's just the partial in terms of x at x naught plus t, comma y naught. If we set t equal to 0, then we have just the partial in terms of x at the point. Okay, so this is a whole nother way of thinking about what this partial derivative is. But in doing this, is there anything special about taking this derivative, just moving along? In this case, we did the x direction. We could do exactly the same thing in the y direction. Is there anything special about just using either horizontal lines or vertical lines? And the answer, of course, is no. Right? So there's nothing special about doing these derivatives in just the x direction or the y direction. Right? So if we're thinking about the point x naught, y naught, so the partials are coming in those ways, but really we could do it any way we want. Kind of the only thing that we need to know is we need to parameterize this line, but to parameterize a line, you just need to know a vector around it, right? And in our case, we're going to choose, we want to choose u to be a unit vector on the line. And we'll talk a little bit about why we want this to be a unit vector. Okay, and so this is going to define what we're going to call the directional derivative of f. So we're going to let u be a unit vector, ab, so a squared plus b squared equals 1. And then we're going to define the directional derivative of f along u. So this means going along a line on the xy plane, going in the direction of u through x naught, y naught. And what that directional derivative is going to be is, well, we have it here as this limit formula, so this is kind of mirroring what we saw in for the definition of the partial derivative in terms of x. So why exactly do we want it to be a unit vector, AB? Well, this denominator here, talking about the denominator delta t here, this denominator delta t, really what this is talking about, if you think about this in Calc 1, this really was the distance between, x plus delta x minus x, right? But then how do you do distance in one dimension? You just subtract them from each other. In multivariable now, our distance formula is a little bit different. So what this delta t is coming from is that if I take the distance between x naught plus a delta t and y naught plus b delta t and x naught, y naught, that's going to look like x naught plus a delta t, but then minus x naught, quantity squared, plus y naught plus b delta t, then minus y naught squared. Going through this, the x naughts cancel, the y naughts cancel, and so this simplifies down to a squared delta t squared plus b squared delta t squared. I can pull out the delta t, I'm left with a squared plus b squared on the inside, but because u is a unit vector, this a squared plus b squared is just equal to 1, and so that's why we just have delta t on the bottom. So delta t on the bottom comes from the distance formula between these 2 points. So that's why we want to use a unit vector. The unit vector is going to guarantee that the distance between these is just delta t. Okay. And so this is the formal definition of it. But as we saw before, we can think about this using the, right? So same as before, this time if our parameterized line is going to look like x naught plus at, y naught plus bt, then this directional derivative is going to be what happens when we plug in this parameterization, take the derivative in terms of t, and then set t equal to 0. Okay, and so if you go through and do this, if we think about what this would actually equal, So we're thinking about taking d dt of f of x naught plus at, y naught plus bt. What do we get? So it would be f of partial in terms of x at x naught plus at, y naught plus bt times the derivative of the x component in terms of t, which would just be a, plus fy x naught plus at, y naught plus bt times the partial of the y component in terms of t, and that would just be b. And then when we set t equal to 0, these guys are just going to go away. And so this is kind of the idea on how we can evaluate these. Okay, so let's do an example. So our function is x squared minus xy, and we want to find the directional derivative in terms of the vector 3/5, 4/5. And so you can double check that that's a unit vector, and we're doing this at the point 2, 4. Right, so our line here is 2 plus 3/5 t, 4 plus 4/5 t. Along the same lines of why we're using a unit vector, it turns out that because we're using a unit vector, this is the arc length parameterization here. So we really are getting a slope because we're getting a change in the z value per distance traveled on the xy plane. So this really is giving a true slope in that sense. Distance in terms of z divided by distance in terms on the xy plane. And so when we plug this in, we're going to be taking the derivative of, so plugging this in here, we're going to have, let's just actually plug this in, 2 plus 3/5 t squared minus 2 plus 3/5 t, 4 plus 4/5 t. Okay, so taking the derivative of this, first term, I'm going to get 2 times the inside. 2's coming down from the power rule, and then by the chain rule, I need to multiply by 3/5. Over here for the second term, by the product rule, derivative of the first is 3/5 times the second. So the whole thing is minus, so I have then plus the first times the derivative of the second would be 4/5. Okay, so there's our derivative. And now we set t equal to 0. I'm going to have 2. This turns into 2 again, times 3/5 minus, I have 3/5 times 4 plus 2 times 4/5. So I have 4 times 3 is 12/5 minus 12/5 minus 8/5. That should be a minus there. And so the two 12/5 cancel off, and so at the end we have minus 8/5 is our directional derivative. So this is d 3/5, 4/5, f 2, 4. So this is saying that if we're going in the direction of 3/5, 4/5, the function is actually going down there. Okay, so if you go through and think about what happens at the end, this is exactly what we saw when we went through the derivation. The the directional derivative in the direction of u at the point is going to be the value of the partial, of the x partial at that point times a. A's coming because that's what we're going to get when you take the derivative of the x component, plus the partial of y at the point times b. The b's coming from that's what you get when you take the derivative of the line in terms of b. Right? Well, if you look at this, so partial in terms of x times an x component of u plus a partial in terms of y times the y component of u, and then they're getting added together, that looks an awful lot like a dot product. Right? And so in fact we can write this as a dot product, right? Where AB, that's coming from u, and what is it getting dotted with? Well, a vector where the x component is the partial in terms of x, and the y component is the partial in terms of y. Well, so now that we know this, well, if we're thinking about this in terms of the directional derivative, the u part is what's changing here. This vector right there, that's going to stay the same no matter what u is. Right? And so then we can ask, so we're dotting two vectors together, what unit vector is going to make this directional derivative, is going to have the largest directional derivative? Okay. What unit vector would we pick to make this as big as possible? Right? And so we're thinking about taking this vector right here, dotting it with another one. What direction do you pick to make the dot product as big as possible? And so we've talked about this, although it's been a number of videos ago, but just, as a review back on properties of dot products, Fy, it's not y naught. If we're taking this and dotting this with u, well, this is going to be equal to the magnitudes of these guys, and so the magnitude of u is just 1, times the cosine of the angle between them. So maximizing this directional derivative is equivalent to maximizing cosine. When's cosine the biggest? Well, cosine is the biggest, is maximized when theta is equal to 0. And so the angle is equal to 0, so that means u is in the direction of this vector of those two partials, right? And so to get a unit vector in that direction, so this is the unit vector u that we want to pick, well, we're going to take this vector and divide by its magnitude. As you can see, this vector, this vector of partial of x comma partial of y, put the partials of y in there. This is an important vector. In fact, we're going to be using it more later on. We got to it by doing these directional derivatives, but it's also, as we just see, it's also telling us which direction the function is growing the fastest, and that's always an important question in calculus. But so far it's been taking me a long time to write it, and so we should just come up with a name for it and with shorter notation, and so that's what we're so this vector, where the x component is the partial in terms of x, the y component is the partial in terms of y, this is called the gradient. And the notation for it is it's sort of like an upside down delta f. Okay, and so this is sometimes called grad. The symbol has all sorts of different names, but it's an upside down triangle in a sense. So we did it here for 2 variables. You can do it for 3 variables. It's exactly the same idea. The gradient of f in terms of 3 variables is going to be the partial in terms of x, the partial in terms of y, the partial in terms of z. Has the exact same properties. You can do directional derivatives in exactly the same way. You're going to get this gradient popping out in exactly the same way. It makes a lot of sense. And so we've already seen lots of important properties of this gradient. So first of all, this gradient evaluated a point. It tells us the direction in which f is increasing the most at x naught, y naught. And in fact, if we go back through and figure out how much it's growing, so the rate of growth there, well, it would be the gradient dotted with a unit vector in the direction of the gradient. And when you simplify that out, you get just the magnitude of the gradient. So the magnitude of the gradient tells us how fast it is going in that direction, and that is the steepest slope. So one of the ways that I think about the gradient is, if you sort of imagine that you're hiking on a mountain and you had a special compass that pointed on to the gradient of the surface that you're walking on. Well, the way that it would point is whichever way is the steepest way up at that point. So it's not necessarily pointing to the top of the hill, but it's pointing to whatever way is steepest there. So if you're thinking about you're on some big mountain range like this, and you're sort of at this point here, it's going to be pointing and saying this is the steepest way at that point right there. Okay. And then we got to this gradient by doing the directional derivatives. So this gradient is going to give us a fast way to do these directional derivatives. If you want the directional derivative of f in the direction of u, you just take the gradient at that point and dot it with u. So let's do 2 more directional derivatives and see how fast this is. So let's calculate. So we have the same function. So our gradient here, partial in terms of x, is 2x minus y. Partial in terms of y is just minus x. And so when we plug in 2 and 4 into this, I'm going to have 4 minus 4 is 0. And then the y component is going to be minus 2. Let me write it so you can see it clearly. 2 minus 2. So that's going to make things pretty easy to do these directional derivatives. And so then if we want, it's actually going to take me longer to write them down than it is to figure out what they are. So if we're doing in the direction of 1 over square root of 2 comma minus 1 over square root of 2. So if you think about that, that's in the 3rd quadrant. So that's at so 180 plus 45 degrees. So that's at 225 degrees. 2, 4. So this is going to be 0, comma 2 dotted with 1 over square root of 2 minus 1 over square root of 2. And that's going to be 0 plus 2 over square root of 2, which is just the square root of 2. And then for the second one, we're doing it minus 1/2 square root of 3 over 2. So this is the 2 pi over 3 in radians, or 120 degrees. And so this is going to be 0, comma minus 2 dotted with 0, comma square root of 3 over 2, which gives us minus square root of 3. Okay, and so using the gradient, these directional derivatives are really fast to do. And this is really the way to go about doing it in the future. That is all for right now. I will see you again soon.